Hi there, this is Glenn Dane. Say I'm doing a little lesson here, professional development, primarily for high school teachers, working through the ASM Education Foundation. This is really in conjunction also with LIFT, our Center Institute on Lightweight Metals Technology. It's part of the National Network of Manufacturing Innovation. Our institute is located up in Detroit, Michigan in particular. What I want to talk about really is the value of lightweighting, really not so much in cars but in vehicles in general. And this is really intended to do two things that are shown on the other slide. One, I wanted to be able to show you how to do simple math with complex units. To me, this is one of the most important things a high school student could know if they want to go into a technical career of any type. If you know this, you're halfway to being an engineer. No kidding. So many things you can do with units. And we're going to look at a particular question and answer questions like, if I can save some number of pounds in a vehicle by putting some kind of advanced component in, maybe a lightweight aluminum component, cast magnesium component, even carbon fiber. It usually might cost you a little extra money to do that. Is it worth it in the fuel savings? So we can do this with math. But we've got to do the math first, and then we'll get to answering the question. Okay. So here's the basic idea, and one could spend a lot of time on this, but again, I want to keep these movies relatively short. When we do engineering calculations, there are really a small number of fundamental physics units, really 7 of them, and almost everything else can be generated from that. We've got mass in the SI system. The standard is a kilogram. We've got meters, which is length. We've got light, which is candelas. We've got time. Seconds is the standard unit for that. Amps is current. Kelvin is temperature. Moles are atoms. Those are the systems, and there are different systems that might express mass differently, length differently. For example, mass or force might be determined in pounds. Length might be in feet. And we go back and forth between these unit systems. We'll talk about how we can do that. And then from these fundamental units, you can get all of these others and a lot more: force, energy, power, pressure, magnetic field. And that's where that comes from. Again, it's a lot more depth one could go through. And then there are our standard multipliers on these. Mega, M for 10 to the 6, giga for 10 to the 9, and down to nano, 10 to the minus 9. And these are the common prefixes that we use in the metric system in particular. So we always put units on numbers when we're doing real physical calculations. And the thing we want to do is take the units and treat them as if they're variables or numbers. That means we can cancel from numerator to denominator. And both sides of the equation have to have the same units. And if they don't, something is wrong. So that's an important check. And boy, I tell you, it's all the time in PhD level exams, we ask these questions. Can you show me the units on that? Does it make sense? Do the units cancel? And this is a thing we ask all the time. And the units have to make physical sense. Adding apples to horses doesn't work. Add apples to apples, or maybe apples to other fruit. You have to have your units make sense somehow. Apples to feet obviously don't add. But if you do engineering calculations, it's easy to make these mistakes, and getting your units correct is really important. So what we're going to do is do unit conversions. There's really 2 key ideas in this. One is you keep the units and you cancel them. Then you can always multiply by 1. For example, 60 seconds per minute, 60 seconds over a minute is equal to 1, or a minute over 60 seconds is equal to 1. We know that 2.2 pounds is a kilogram, so 2.2 pounds per kilogram is equal to 1, or 1 kilogram divided by 2.2 pounds is equal to 1. We can do the same things with miles. You can make a multiplying factor of 0.62 miles is the same as a kilometer. And so we can do things like that. So we can ask ourselves simple questions, like, for example, how many, use my microphone there, it fell off. How many seconds might there be in a year? How many seconds? How many seconds in a year? So we can say 1 year is equal 365 days per year, and we've got 24 hours 24 hours per day. We've got 60 minutes, I should say, per hour. And we've got 60 seconds. I don't know what happened there. 60 seconds per minute. Start canceling units here. Days cancel. Let me change my colors as much as anything because I can. Hours cancel here. Minutes cancel here. And when you work out the math, what you end up getting, and unfortunately I did my notes. I did this in how many seconds per day, so I've got to do a little multiplication. When you do this, it's 86,400 seconds in a day, and if you work that out, you get 31,536,000 seconds per year, and the units, seconds, and year end up right there, okay? And I should write this right next to that rather than beneath it, okay? So that's your answer, 31 million seconds per year in that simple thing. And again, this is just, the important thing here is each of these fractions is basically equal to 1, and then you can cancel them out. You can do simple things with this. You're riding a bicycle, you're going to go 30 miles at 12 miles an hour. So 30 miles divided by 12 miles per hour. Do the same thing. The miles cancel. The hours was on the denominator of the denominator, makes it back to the numerator, and you get 2.5 hours out of that. We could ask another question. Say you want to go 100 miles, your car gets 27 mpg, and gas is $2.86 a gallon. How much does it cost you to do that? 100 miles divided by 2.7 miles per gallon multiplied by $2.86 per gallon. Work that out. Miles cancel there. I'll do it in a different color. Gallons cancel here. And again, this is on the denominator of the denominator goes to the numerator, therefore it can cancel with that denominator. And when it's all done, you get in units of dollars, 10.59 is what it costs you. And again, it makes the point that thanks to all the engineering feats we've done, transportation is pretty inexpensive. Down at the bottom here also I've got some websites that you can use, Wikipedia and YouTube. There's lots of good stuff on this if you want further detail on it. A couple good ones are shown. I can obviously give you more if you like. Okay, let me get into how this works with mass reduction in vehicles. Again, the common metric we use for looking at fuel efficiency of a vehicle is miles per gallon. That's maybe not a great one because if you have a smart car that can only fit 2 people, it looks like it's pretty efficient, but if you've got a bus that burns a lot more miles per gallon, but you can get 80 people on it or 30 people on it, that might be a lot better in terms of passenger miles per gallon. That's a much better metric. Another thing you might use is energy per distance, how much energy measured in megajoules per kilometer does it take. The other one that I'm going to use that's particularly useful, I think, is the energy it takes to send a given mass a given distance. So this is energy per mass per distance, and we can do this in terms of kilojoules, which is a unit of energy, per kilogram per kilometer. And we'll turn this into units that are kind of useful. You can find good data on this. If you look, Mike Ashby, a professor at Cambridge, has a really nice book, Materials in the Environment. And he has data that's shown in there for different modes of shipping. And it turns out if you have big diesel ocean liners or big diesel rail shippers, these accelerate your cargo once, takes very little energy to keep it going. And you can get units here or figures for about how much energy it takes to send an extra mass, an extra distance. That's at one end of it. Personal auto, you got a number in here. Helicopters and air freights are much at the other end. These take a lot of energy. If you're going to deliver something by helicopter or drone, you've got to take it, pick it up in the air in a vehicle that's pretty inefficient, pretty weight sensitive, and burns a lot of fuel to do that. So how do we make sense of this? How do we take numbers like this and make sense of them? Well, let's look at savings reduction from auto mass. And the approach we're going to use with this is take this metric, the Ashby thing, energy is mass times distance, and then multiply that by how long that vehicle might last, and then you could have an energy savings per mass. And this can help you answer the question, if it costs me $10 to put in a component that saves me 10 kilograms, is that worth it? So we're going to do this first for an automobile. And before I said we have this unit that costs you about 2 kilojoules to send an extra kilogram, an extra kilometer. And so I can take that and multiply that number by the life expectancy of a car, which I have here is about 200,000 kilometers, about 130,000 miles. That's about the number of miles I've got on my Subaru right now. And so just multiply, one extra kilogram times that factor times life expectancy of a car. I get 4 times 10 to the 5th kilojoules. I can multiply that by 1 megajoule is 1,000 kilojoules, and then I get 400 megajoules per kilogram out of that. And then I can take this thing, I get 400 megajoules per kilogram. On the last slide I also showed you that there's about 130 megajoules in a gallon of gasoline. So I can take 400 megajoules per kilogram, divide this by 130 megajoules, and notice that gallons are on the denominator of the denominator there. So megajoules cancel, and I get, by saving that 1 kilogram in a vehicle, I save about 3 gallons of gasoline over the life of the vehicle. I can put a real cost on that too. So gas is about $3 a gallon. So what we end up getting out of this is two things. We could figure out how much fuel is saved per kilogram of mass savings. About 3 gallons of gasoline is saved for every kilogram. And you could turn that into another unit. You're saving about $4.50 per pound of mass in the vehicle over its life cycle. So we can reduce the mass of a vehicle. For example, the Ford F-150 from going from steel to aluminum saved about 700 pounds. You can see that turns into significant money. And these are, again, order of magnitude sorts of calculations, but they're real. And you can see that you can expect to save a lot of money from fuel by these lightweighting decisions. If we do this for an airplane, we can do the same thing, except we have different numbers in here. For an airplane, there's a much higher number. It's about 10 kilojoules per kilogram per kilometer. That's on the low side. And airplanes go at least 10 million miles, usually much more than that. So if I do the same sort of approach, put this in, we have 1 kilogram multiplied by this energy burn rate, multiplied by the life expectancy of it, I get about 1 times 10 to the 8, about 100 million kilojoules is saved. That's about 100,000 megajoules is saved. Again, gasoline is about 130 megajoules per gallon. So we're ending up saving about 800 gallons of gasoline over the life of an airplane by pulling a kilogram out. It's a big deal. This is why the airlines care how much your baggage weighs. They actually care about how much you weigh too, but they figure that's a little bit personal. They don't want you carrying extra baggage because it costs them real money, and if you imagine that extra weight is in there every flight, boy, that costs them a lot of money. So in an airplane, you can save about 800 gallons of gasoline for every kilogram that's saved. So math savings in this case is worth about $1,000 a pound. And so we can see the two important things in this is this rate at which energy is burned, and the life expectancy of the vehicle in terms of distance. So this is a little bit of a complicated graph, but it shows for each of these things I can have this transport energy that I get from Ashby's book, and this is on a logarithmic scale here. And I have a service life here, and I can put different things on here. You know, an economy car might be a little more fuel efficient than an SUV. You can argue what the service life is. Certainly things like diesel rail go long distance and have low burn rates. And you can figure out where these things sit, and basically as you go out this way, this means that there's going to be extra value in saving mass. So things like airplanes, there's huge value in that. Things like cars, not as much. And each of these lines on this log scale turn into an area where you've got a constant value of cost savings per pound taken out. So for cars, it's maybe between $1 and $10. For airplanes, it's between about $1,000 and even $10,000. So, and you can put other sorts of vehicles on there and use the same sort of math to go through that. And again, that's a little bit of an advanced approach of this, but it's just basically the same thing. Okay, so I'm going to connect this to what this means in terms of materials selection. So let me look at the top of this thing is all vehicles. In the middle, there's a log scale. And down at the bottom, there are various materials. So we can actually put vehicles on a scale of dollars per pound. It turns out cars, if you get an ordinary consumer car or a truck, there may be $5, $8 a pound, up to $10 a pound. You get a sports car, a really nice one, they might be $50 a pound. You buy a commercial jet, take the purchase price divided by the weight of the vehicle of the jet, you're up around $1,000 a pound. And we can compare that with the prices of materials. This is cheap materials down here, very expensive materials over here. And again, there are a huge range. Gold, diamonds, platinum up here, extremely expensive, thousands of dollars per pound. Concrete is about $1 a pound. But even among materials, there's real differences. Steel is about half of that on a per pound basis versus aluminum. Magnesium costs a little bit more. Carbon fiber costs quite a bit more, usually $10 a pound or up. Point being that there are certain vehicles where, like a commercial jet, if a pound saved can save you $1,000 over the life of that jet, it makes complete sense to use things like carbon fiber, even if they are expensive, because it saves you that much fuel. If you have something like a family car where it's costing you on the order of $7 a pound, the difference between steel and aluminum can be important in terms of an economic decision, and it can be very difficult to economically justify carbon fiber at current prices. This is part of why metals make a lot of sense for next generation vehicles. Eventually carbon might become cheaper and easier to use and more will be deployed. So all of this does turn into economic decisions, and that's what I hope also to show with this is there are economic decisions. Data's out there. If you do the math, you can easily figure out what makes sense. So let me sum up here. 2 big points. If you can reduce the mass of vehicles, it really changes the amount of energy that's used. And then secondly, if we know how to use units and math and get data, we can make good estimates. And if we're doing things like cars, it's usually several dollars per pound saved. If we do something like a commercial airplane, we can save thousands of dollars per pound saved because that airplane is always in the sky. It's always accelerating, getting into the sky, coming back down. A little bit of weight savings changes the amount of energy burned over time tremendously. That's it. Thanks for watching, and look forward to further interactions with you all. Let me try to close out here. Holy cow. End show. Discard notes. Bye-bye.